You can draw a perfect straight line across your chart on the ground, but the moment your wheels leave the runway, the atmosphere takes a vote. Unforecasted winds will immediately begin pushing your aircraft off that planned track. If you aren't paying attention, a slight crosswind over a vast, barren landscape can easily push you miles off course, leaving you drifting blindly without clear reference points to find your way back. To stay exactly where you belong, you need to execute a regular, repeatable routine, the 15-minute en route navigation check. This cycle allows you to pinpoint your exact position, update your actual ground speed, and correct your compass heading. Before you even look down at your map, you have to stabilize the aircraft. Trim the flight controls so the aircraft can maintain its altitude and heading completely hands-off. Once the plane is flying itself, you can stop hoping the weather forecast was right and start using visual evidence to establish the mathematical reality of your flight path. Step 1 is orientation. Look at your chart and physically rotate it on your lapboard so your desired course points straight up. Now, whatever you see on the right side of the paper will appear out the right window of the airplane. Next, check your written flight log. Find the exact estimated time of arrival, or ETA, for your next chosen landmark. You don't need to stare out the window the entire leg. Wait until you are 2 to 3 minutes away from that calculated ETA, then begin a visual scan roughly 30 degrees to the left and right of your nose. By anticipating exactly when and where your target will appear, you keep your eyes focused outside, sharply reducing the time your head is buried inside the cockpit. When a potential landmark comes into view, your first job is to match its size and shape to the corresponding symbol on your map. But finding a match isn't enough. You have to apply the relationship rule. From the air, many lakes and towns look identical, so you must confirm your target by checking its relationship to a secondary feature nearby. For example, this diagram shows 2 similar towns. To verify you are looking at the correct one, you check for the single-track railroad to the west and the road crossing the river to the north. If those elements match, you have the right place. Linking a primary town with its neighboring roads and rivers creates a positive, indisputable geographic confirmation. Skipping this verification step and locking onto the wrong town will throw off every subsequent calculation you make, turning a minor drift into a major navigational error. Once you identify your location, you can chart it. If you cross a long, narrow feature, like a highway or a railroad, you have established a position line, meaning you know you are somewhere along that specific line. To get a true fix, you must either fly directly over a specific point or cross 2 intersecting position lines. This top-down map shows an exact fix logged right over a prominent road intersection. The moment you establish this fix, grab your pencil and log the exact time in UTC directly on the chart next to your position line. Now that you have a confirmed time and distance on the map, you can figure out how fast the wind is actually pushing or pulling your aircraft. Look at the bracket spanning the gap between your last fix and your current one. If you covered 18 nautical miles in exactly 8 minutes, simple division reveals your actual ground speed is 135 knots. Take that 135 knots, return to your written flight log, and recalculate the estimated time of arrival for every remaining checkpoint on your route. By forcing yourself to physically map the fix and write down the exact minute you crossed it, you turn abstract estimates into a concrete measurement of your forward progress. Along with checking your speed, plotting that fix will usually reveal that the wind has pushed your aircraft slightly left or right of your original course line. This diagram illustrates exactly how to correct for that drift. You measure the angle between your desired course and your actual track, known as your tracking error, and add it to the closing angle, which is the trajectory you need to fly to rejoin your route. For visual navigation, we simplify the math. As long as the required correction is under 15 degrees, that total course change can be applied directly to your compass as a heading change. Make these mental calculations quickly. Do the math, dial in the new heading, and get your eyes back outside. Do not let minor charting corrections distract you from safely flying the airplane. Applying these small 5 to 10 degree heading corrections early in the flight prevents you from having to make sharp, disorienting turns to find your destination later on. Completing this sequence gives you total control over the flight. You have a verified position on the map, a precise arrival time for your next waypoint, and a wind-corrected heading on your compass. You do not need to continuously monitor the map second by second. Navigation is a rhythm. You execute this check, fly the plan, and repeat the process every 10 to 15 minutes. In the downtime between those fixes, you run through a quick system sweep, known as FRIHA. Check your fuel levels, your radio frequencies, monitor engine instruments, heading indicator alignment, and altimeter setting. By compartmentalizing your tasks into predictable cycles, you maintain perfect situational awareness without becoming overwhelmed. That structured rhythm is the foundation of safe, precise cross-country flying.